So here's the question we're going to do here. We're going to first find the derivative of y equals e to the x over x. Then we're going to find the slope of the tangent at x equals ln 2. And then the big question here, we're going to find any local maximum and minimum points of the function. So let's start with part A here, finding our derivative. If we want to find the derivative of this function, there's one thing we should do before we start taking the derivative here. We should look for a way that we can rewrite this function that'll make the derivative a little bit easier. So we've got a quotient here. Let's rewrite this as e to the x times x to the negative 1. So we can use the product rule instead of the quotient rule. So our derivative is going to become, well, let's see. Product rule, we've got u and we've got v. So we want the derivative of u times v plus u times the derivative of v. Derivative of u, e to the x, is just e to the x. So e to the x times x to the negative 1 plus u, again, e to the x, times the derivative of v. Derivative of v, we're going to bring down the negative 1 to have negative 1 x to the negative 2. And then probably, if they're just asking us for the derivative, we're going to try to simplify this thing a little bit here. So we can factor out e to the x. We can factor out the lowest power of x here, which is going to be x to the negative 2. And that's going to leave us with an x and a negative 1 inside the brackets. So this would be e to the x over x squared x minus 1. That's sort of the most simplified form of the derivative that we could have. Now, part B asks us to find the slope of the tangent at x equals ln 2. Now, the only reason I'm showing you this is just to make a point about what happens when you have values that involve, you got x values that involve natural logarithms here. All we need to do is we just need to sub in this expression, ln 2, anywhere we have an x. So our derivative is going to become e to the ln 2 divided by ln 2 squared times ln 2 minus 1. We're not going to take ln 2 and punch it into our calculator and get a decimal. We want to leave these things as exact values. So we're going to leave this ln 2 here as a ln 2. We're going to leave this ln 2 squared down here as ln 2 squared. The one piece of simplification that we're going to do here is we have e, our natural base, and then if in our exponent we have a natural logarithm. So anytime you have an exponent with some base, and up in the exponent you have the logarithm of the same base, base is e in both cases here, you can think of those two things as canceling each other out. Okay? So if I have e to the log e, that cancels out, and I end up with 2 over ln 2 squared times ln 2 minus 1. You could do the same sort of canceling if you had 10 to the exponent log to the base 10 of 2 or something like that. Okay? All right. Now, our big question here is part C. We want to find our local maxima and minima. So what do we need first if we're finding local max and min? What do we look for? Critical numbers. So our critical numbers are going to be where our derivative equals 0 or our derivative does not exist. What is our derivative here? Well, we've got this expression e to the x divided by x squared times x squared minus 1. So if we're looking for places where the derivative is equal to 0, recall that we are going to set our numerator equal to 0. And if we're looking for places where our derivative does not exist, we're setting the denominator equal to 0. So our numerator here is we'll set this equal to 0. Our numerator is e to the x times x minus 1. Okay? Because both of those are going to be divided by that x squared term. Now, how do we solve this thing?
Yeah, it can be 0 and x equals 1. So, yeah, x equals 1.
All right, you're on the right track here. We want to take both of these things, and we want to set them equal to 0, and we want to solve these things for x. So this one over here is really easy. X minus 1 equals 0 just gives us a solution that is x equals 1. E to the x equals 0 is the tricky one. Okay? Robin, you mentioned that if x was 1, what happens if x is 1 here? Yeah, it's going to be e to the 1, which is about 2.71. Okay? How can we solve this thing here? We can't. There is no solution here. Think back to what, I'm going to add a little page in here. Think back to what an exponential function looks like. Okay? It has a horizontal asymptote at y equals 0. Okay? So this thing approaches y equals 0, but it never quite reaches it. So it doesn't actually, it's never going to take on a value of 0. So if we get something like this, e to the x equals 0, we can just say that there is no solution to this. Okay? And if we want, we can cross it out to remind ourselves that that's not a critical point. Okay, moving over here to where our derivative does not exist. We're going to take our denominator, x squared, and set it equal to 0. Can we solve this thing here? Yes, what is our solution? X equals 0. We have to be careful with solutions like this, where things don't exist. What happens if we take x equals 0 and we go back to our original function and we sub it in? Original function is y equals e to the x over x. If we put in x equals 0, what happens? It does not exist. So this point, even though it looks like it's a critical number, it's not in the domain of the function. Okay? So there's a vertical asymptote for this function at x equals 0. If we were setting up an interval table and we were looking for the intervals of increase and decrease, we would use this as one of our critical numbers in our interval table. But we're not asked for that. What we're asked for here are local maxima and minima. So this x equals 0 cannot be a maximum or a minimum point because the function doesn't exist there. So it's not in the domain. I'll just say can't be max / minimum point. Okay? So we're not going to really look at this critical number either. So we're left with just one point, x equals 1. This is our only possibility for a local maximum or local minimum. How can we figure out whether this is a local maximum or a local minimum? We can use the second derivative test. Now, you don't have to use the second derivative test. You could have used the first derivative test, set up your interval table, at which point you would probably make sure that you considered values of x that were less than 1 but greater than 0. But we can use our second derivative test. Now, this is going to be a little bit tricky because our first derivative is a little bit complicated. E to the x over x squared times x minus 1. What I would do is I would go back to this form of our first derivative here, where we've got everything written out as, you know, something times something plus something times something else. And that's the form that I would start from. So that's where I'm going to pick it up here. I'm going to say that y primed is equal to e to the x times x to the negative 1 minus e to the x times x to the negative 2. Okay? And all I've done is I've just taken that negative 1 and turned it into a minus sign in between. And I think this time around, I'm going to put in some round brackets here and here to sort of break this up so we can better keep track of where we are. Because you can see from this that what we're going to have to do is use the product rule twice. Once on that first bracket and once on that second bracket. So let's give this a shot here. Our derivative is going to be, let's see, u times v, so derivative of e to the x is e to the x times x to the negative 1 plus u, which is e to the x, times the derivative of x to the negative 1, so that's going to give us a negative 1 times x to the negative 2. From this, we are going to subtract, okay, this is going to be the whole derivative of this second bracket here. Derivative of e to the x is e to the x times x to the negative 2 plus e to the x, we're going to bring down the negative 2 and multiply, and so I subtract 1 from our exponent, x to the negative 3. So e to the x times x to the negative 1 plus e to the x times negative 1 x to the negative 2 minus e to the x to the negative 2 plus e to the x negative 1, and so on and so on. Okay? And now we just want to simplify this thing, I think, a little bit. We can, let's see, e to the x times x to the negative 1 is just going to be e to the x over x minus e to the x over x squared. So that's those first two terms. And then minus e to the x over x squared. And then minus and minus 2 is going to give us a plus 2e to the x over x cubed. This simplifies a lot when we evaluate it at x equals 1. All those denominators become 1, and our numerators become e minus e minus e plus 2e. So e minus e plus 2e works out to just be e. E, of course, is greater than 0. So our second derivative is positive, which means we have a local minimum. So what we would do then is we would evaluate our original function at x equals 1. So we get y equals e to the 1 over 1, which is just e. So our point is 1 e, 1 comma e, and it is a local minimum. Okay. And we're done.